where it has the electromagnetic field waves propagating inside the telephone cable. And if we can just see that the propagation constant of the telephone line, here the value of z will be like r, and the capital Y will be like j omega c. So for telephone line, the z value, that is the series impedance, as r and y equal to omega c. Thereby the propagation constant of the telephone line, if we calculate, we get the value as gamma, where gamma equal to root 2j into omega cr by 2. Now if we can just have this particular gamma in terms of alpha plus alpha, we know gamma is alpha plus j beta. So if we just value of alpha and beta, so we get alpha and beta as the same value for the telephone cable. So alpha, that is equal to beta, and then the value is square root of omega rc by 2. So the attenuation constant and the phase constant of the telephonic cable is quite similar. And coming to the velocity of propagation of the telephonic cable, so we know that the velocity of propagation v equal to omega by beta. So if we can just substitute, we get the velocity of propagation of the telephonic line as square root of 2 omega by cr. So this is about the telephonic cable. So the alpha and v are the functions of frequency, and thus the higher frequencies are attenuated more and travel faster than the lower ones. This results in considerable frequency and delay distortion in a telephonic cable. Now coming to loading part. So there are two types of loading: continuous loading and the lumped loading. Now continuous loading, if we can just see that we just wound a conducting material on a transmission line. So if we can just have an increase in the conductance uh, continuously over a transmission line, then we call that as continuous loading. So due to that continuous loading, the inductor value will be increased depending upon the material which we are going to just wound onto the transmission line. So the material, so the inductance will be L will be like mu by d by nt plus 1, where mu is the permeability of the material being used for winding, and d is the diameter of the copper conductor, n is the number of layers which we have wounded, and t is the thickness of the layer of tape or the iron wire wounded. Now coming to the propagation constant of that, now the propagation constant gamma equal to root zy, and if we just calculate for the continuously loaded lines, so we get the value of gamma as we can see. So mathematically we try to get that, and actually we have to assume for continuously loaded cable, it is assumed that the value of g is 0 and l is increased such that omega l is very much greater than r. Then the value of z will be like r plus j omega l, but y will be like j omega c, right? And then the value of propagation constant, if we just calculate, so we get that as gamma equal to omega root lc into 1 plus r square by l square into omega square whole power 1 by 4. With an phase shift, we have like pi by 2 minus 1 by 2 tan inverse of r by omega l. That's the propagation constant of continuously 1. If we can just see, now here we can just see here, the propagation constant will be like the propagation constant due to that will be less depending upon the value of theta. And then if we can just see the value of alpha, beta, and the velocity of propagation for the continuously loaded lines, so accordingly if we just try to calculate, so we get the value of alpha as uh, which is independent of frequency, beta is dependent on frequency, and velocity of propagation as 1 by root lc. So this is about the continuous load lining. Okay, and the advantage of this is it is very expensive, because if you are going to wound up every part of the continuous path of the transmission line, so it will be very expensive, and small increase in EL per unit length we achieve, and existing lines cannot be modified by this method. Only replacement will be for this particular method. Okay, this is about the continuous loading. Thank you, and we will see in the next video where we can see about the patch loading. Thank you for listening to this video. Thank you.